All right, by this point, I would hope that you're somewhat comfortable with trig substitution, or at least we've done one example. Maybe you're not super comfortable, but we've got one example done. So we're going to start doing some more today, and don't worry, there will be plenty more to come. I know trigonometric substitution is a pretty hard thing, but we're going to keep going, and it's going to help us at the end find our areas of ellipses and all these really cool shapes. But right now, we're just going to stay in the indefinite world for now. So welcome back to 3 Deviations. In the last video, we just introduced trigonometric substitution and all of its different little substitutions that we can make. In this video, we're going to be building upon that. We're going to be talking about some of the examples of these indefinite integrals that can get pretty darn ugly. So let's get started. Our first example, I would like us to integrate the square root of x squared plus 16 all over x to the fourth with respect to x. Now what we see is we see an x squared plus 16. So let's make our triangle here. Hopefully we're going to be left with enough room, but hopefully. So if we have x squared plus 16, we see a plus there. That should immediately set a little alarm ringing that we have a hypotenuse. So x squared plus 16. And theta is going to be right there. So now we know that we're going to make a substitution. That substitution is going to be x equals 4 tangent of theta. So if we have x equals 4 tangent of theta, then tangent of theta is going to be x over 4. So tangent of theta is SOHCAHTOA, so TOA, opposite over adjacent. So we have the opposite as being x, and the adjacent side as being 4. So now we're all squared away with that triangle, or I guess triangled away with that triangle. And now we can look at our dx. So our dx is going to be the derivative of our x. So we get dx equals 4 secant squared of theta d theta. So there's your differential analysis there. And now we can go into our substitution. Now this is going to look pretty ugly. We're going to get the integral of the square root of 16 tangent squared theta plus 16 over 128 tangent to the fourth of theta times 4 secant squared theta d theta. Now what we can do is we can just simplify, and this is going to end up fairly nice. So we're going to get the integral of 8 times the tangent squared of theta plus 1 over 128 tangent to the fourth of theta times secant squared of theta d theta, which is equal to 8 secant theta over 128 tangent to the fourth of theta times secant squared of theta d theta. Okay, so now we can simplify this. This becomes 8 secant cubed of theta over 128 tangent to the fourth of theta d theta. And now we take out a 1/16. And we take out a 1/16, we get the integral of secant cubed of theta over tangent fourth of theta d theta. We write everything in terms of sine and cosine. So then we get 1/16 integral of 1 over cosine cubed of theta times cosine fourth of theta over sine fourth of theta d theta. We can cross out some terms. This gives us 1/16 the integral of cosine theta over sine fourth of theta d theta. We make a mental u substitution, setting u equal to the sine of theta. This is going to leave us with, well, we add 1 and then we divide by 3. So that gives us really sine to the negative 3, but we can rewrite this as the cosecant cubed of theta. So we get negative 1 over 48 cosecant cubed of theta. Okay, so now all that's left is to find our triangle sides. So we need to find the cosecant cubed of theta. And we can really write this as the cosecant of theta cubed. But once we do that, it's pretty easy. So sine is defined as the opposite over the hypotenuse. So we need to find the opposite, or the hypotenuse over the opposite, which is x squared plus 16 over x. So now we just substitute that in for cosecant of theta. So that gives us negative 1/48 times the square root of x squared plus 16 all over x, quantity to the third power, all plus c. So that is a good trig sub example. This is still pretty simple though. We're going to be getting into the trinomial square roots, but we'll deal with that later. For now, let's just stick with these binomial square roots. So for this example, I want us to integrate the square root of 1 plus x squared all over x dx. Now, again, what we see here is we see a triangle and we also see a plus sign, which means that we're going to be dealing with a hypotenuse for our known. So our known is 1 plus x squared, and our theta goes right there. So we make the substitution, x equals tangent theta, and dx equals secant square root of theta d theta. This leaves us with the integral of 1 plus tangent square root of theta square root over tangent theta times secant squared theta d theta. Now we can also look at our analysis with the triangle. So we can rewrite x equals tan theta as x equals 1 tan theta. So x over 1 equals tan theta. So we have x over 1, rise over run. And now that we're done with that, we rewrite our integral as the integral of secant theta over tan theta times secant squared theta d theta. Now we write everything in terms of this thing that allows us to integrate a cosecant integral. Now, this is something I'm going to give to you now. We're going to cover something called the Weierstrass substitution, which is going to make the integrals of these trig functions like this a lot easier. But until then, I'm just going to give you this integral. Otherwise, it's pretty convoluted and you need to be looking for the exact right substitution, and that's not really how math should work, because you should derive it on your own. So we have the integral of secant theta times 1 plus tangent squared theta over tan theta. So we're expanding with that Pythagorean identity, everything with respect to theta. Now we rewrite this as the integral. We separate fractions of secant theta over tan theta plus sec theta tan squared theta over tan theta d theta. Now we can rewrite this, writing everything in terms of cosecant, secant, and tangent. We want to decompose this here and cancel terms. We can do that, and that gives us the integral of cosecant theta plus sec theta tan theta d theta. Now these are integrals that we know how to do. I will teach you how to do the cosecant integral in a later video right after we do trig sub, but we know how this works because this is just an elementary antiderivative. So this gives us the natural logarithm. So the integral of the cosecant is the natural logarithm of the cosecant minus the cotangent, absolute value, plus secant theta. We add that there because that's our elementary antiderivative. Well, now we need to look at our triangle. So we need to find the cosecant of theta. So that's going to be our 1 plus x squared square root term over our x. So we have the natural logarithm of the square root of x squared plus 1 over x. Now we subtract that from this cotangent of theta. So cotangent of theta is run over rise, so 1 over x, so minus 1 over x. We end that absolute value, and then we add the secant of theta. So the secant of theta is the hypotenuse over the adjacent, which is just 1 plus x squared because we're dividing by 1. Then we add a constant of integration, obviously, for all of our sanity, or else our calculus teacher might not be too happy. Okay, well, thank you so much for watching this video of 3 deviations.